40. References 49. Clydesdale, F.M., Gover, R., Philipson, D.H., and Fugardi, C. 1992. The effect of color on thirst quenching, sweetness, acceptability and flavor intensity in fruit. Punch-flavored beverages. J. Food Quality 15, 1938. Cook, D.J., Hollowood, T.A., Linforth, R.S.T., and Taylor, A.J. 2003. Oral. Shear stress products flavor perception in viscous solutions. Chemistry. Senses 28. 1123. Dallas, C., Ricardo da Silva, J.M., and Laurino, O. 1996. Products formed in model wine solutions involving anthocyanins, procyanidin B2, and acetaldehyde. J. Agric. Food Chemistry. 44, 2402 2407. Dambrook, T., Narkle, R., Marchal Delahort, L., Parmentier, M., Morgan, O. and Jeandit, P. 2003. Immunodetection of protein from grapes and yeast in a white wine. J. Agric. Food Chemistry. 51, 2727 2732. Dubos, C.V., Cardillo, A.V., and Malla, O. 1980. Effects of colorants and flavor. Ants on identification, perceived flavor intensity, and hedonic quality of fruit. Flavored beverages and cake. J. Food SCI. 45, 1393 1399. Dupin, V.S., McKinnon, B.M., Ryan, C., Bowley, M., Markets, A.J., Jones, G.P. Williams, P.J., and Waters, E.J. 2000. Saccharomyces cerevisiae Manipro. Tines that protect wine from protein haze, their release during fermentation. And Lee's contact and a proposal for their mechanism of action. J. Agric. Food Chemistry. 48, 3098 3105. Edelani, M. 1966. Study on the stabilization of sparkling wines, in Hungarian. Borgazdazug, 12, 3032, reported in Amarinit al., 1980. Fulkrand, H., Bin Abdeljalil, C., Regord, J., Jnia, V., and Mutaunit, M. 1998. A new class of wine pigments generated by reaction between pyruvic acid and grape anthocyanins. Phytosh Mystery 47, 1401 1407. Fulkrand, H., Shania, V., Osmiansky, J., and Mutaunit, M. 1997. The oxidized tartaric acid residue as a new bridge potentially competing with acetaldehyde in flavin 3-ol condensation. Phytosh Mystery 46, 223227. Gijan-Furtner, K.R., and Kipper, D.C. 2003. Color Vision. A New Revelation. Neurosci. 26. 181206. Glories, Y. 1984. La couleur des vins rouges. 2e Party. Mesure, Origin it Interpreter. Shan. Con. Vin VIN 18, 253271. Hitters, R. Yebra, Y. Perez, MM, Melgosa, M., and Niguirula, I. 2003. Color variability for a wine sample poured into a standard glass wine sampler. Color res. Apple. 28, 473479. Island, PG, and Marquise, N. 1993. Pinot Noir, viticultural directions for improved fruit quality. Proc. 8th Ost. Wine Ind. Tech. Conf. Adelaide, 13-17 August. 1992, P. J. Williams, D. M. Davidson, and T. H. Lee, eds. pp. 98-100. Wine. Titles, Adelaide, Australia. Jackson, R.S. 2008. Wine Science, Principles and Applications, 3rd ed. Academic Press, San Diego, CA. Kaiser, P.K., and Boynton, R.M. 1996. Human Color Vision, 2nd ed. Optical Society of America, Washington, D.C. CUNY, R.G. 2002. CE 2000, Milestone or Final Answer. Kernel. Res. Apple. 27. 126127. Chapter 2, Visual Perceptions 50. Leon, K., Domingo Miri, D., Pedrischi, F., and Leon, J. 2006. Color Measurement in LAB units from RGB digital images. Food Res. Int. 39, 1084 1091. Ligabulaire, G., Marchal, R., and Jeandit, P. 2002. Close-up on bubble nucleation in a glass of champagne. J. Inol. Vitic. 53, 151153. Lubbers, S., Ledger, B., Charpentier, C., and Feuillat, M. 1993. Effet colloid pritk. Tur d'extraits de peroid de levure sur la stabilité tartrique d'en solution hydro. Palculic model. J. Int. SCI. Vin VIN 27, 1322. Maga, J. 1974. Influence of color on taste thresholds. Chemistry. Senses Flavor 1. 115119. Martin, MLGM, G. W. Luo, R. Hutchings, J. and Heredia, F.J. 2007. Me. Showing color appearance of red wines. Food Quill. Brief. 18, 862871. Morgan, A., Hay, B., and Bureau, G. 1978. Étude sur un phénomène de masque. Observe en Champagne. Vinron Champenoy 99, 308313. Mazza, G., Fukumoto, L., Delacqui, P., Girard, B., and Urt, B. 1999. Anthoshire. Nins, Phenolics and Color in Wine from Cabernet Franc, Merlot and Pinot Noir in British Columbia. J. Agric. Food Chemistry. 47, 4009 4017. Morat, G., Brochet, F., and Dubadieu, D. 2001. The Color of Odors. Brain Language. 79, 309320. Munsell, H. 1980. Munsell Book of Color, Glossy Finish. Munsell Color Corpo. Russian, Baltimore, MD. Niguirula, I. Eshavari, J.F., Los Arcos, M.L., and Lopez de Castro, M.P. 1990. Study of color of quaternary mixtures of wines by means of the skiff. Design. J. in all. Vitic. 41, 232-240. Niguirula, I., Echevarri, J.F., and Perez, M.M. 1995. A study of correlation between inological colorimetric indexes and CIE colorimetric parameters in red wines. J. in all. Vitic. 46, 353356. Neogi, P. 1985. Tears of wine and related phenomena. J. Colloid interface SCI. 105. 94101. Nurgle, C., and Pickering, G. 2005. Contribution of glycerol, ethanol and sugar to the perception of viscosity and density elicited by model white wines. J. Texture. Studies 36, 303323. Osterbauer, R. Matthews, P.M., Jenkinson, M., Beckman, C.F., Hansen, P.C. and Calvert, G.O. 2005. Color of sense, chromatic stimuli modulate odor responses in the human brain. J. Neurophysiol. 93, 3434 3441. Pa, W.V., White, K.G., and Heatherbell, D. 2003. The Nose, Influence of Color on Perception of Wine Aroma. J. Wine Res. 14, 99121. Pellerin, P., Waters, E., Brillau, A., J. M., and Moutounit, M. 1994. Effet de Polissac. Charite sur la formation de troubles protique dans UNVIN blanc. J. Int. SCI. Vin. VIN 28, 213225. Peng, Z., Duncan, B., Pocock, K.F., and Sefton, M.O. 1999. The influence of ascorbic acid on oxidation of white wines, diminishing the long-term anti-browning effect of SO2. Ost Grape Grower Winemaker 426A, 6769, 7173. Perez Magarino, S., and Gonzalez San Jose, M.L. 2002. Prediction of red and rose wine CIE lab parameters from simple absorbance measurements. JSCI. Food. Agric. 82, 1319 1324. References 51. Pocock, K.F., and Waters, E.J. 1998. The effect of mechanical harvesting and transport of grapes, and juice oxidation, on the protein stability of wines. Ost. J. Grape Wine Res. 4, 136139. Pointer, M.R., Attridge, G.G., and Jacobson, R.E. 2002. Food color appearance. Judged using images on a computer display. Imaging SCI. J50, 2537. Poccani, J., Philip Kem M. and Pudil, F. 1998. Prediction of odor and flavor exhib. Tances of white wines on the basis of their color. Narang 42, 412415. Rankine, B.C., and Pylone, D.O. 1973. Saccharomyces bailey, a resistant yeast, causing serious spoilage of bottled table wine. J in all. Vitek. 24, 55, 58. Rensk, M, Schwartz, M, and Winterhalter, P. 2007. Pyranoanthocyanins, an overview on structures, occurrence, and pathways of formation. Trends Food. SCI. Technol. 18, 526534. Ruberio Geon, P., and Glories, Y. 1987. Phenolics in Grapes and Wines. Proc. 6th. Ost. WineInd. Tech. Conf. Teely, ed. pp. 247256. Australian Industrial. Pub, Adelaide, Australia. Robinson, W.B., Weirs, L.D., Bertino, J.J., and Matic. L.R. 1966. The relation of anthocyanin composition to color stability of New York State wines. J. In all. Vitek. 17, 178184. Sakai, N, Imada, S, Saito, S, Kobayakawa, T, and Deguchi, Y. 2005. The effect of visual images on perception of odors. Chemistry. Senses 30, Supple 1, I244 I245. Sabat, K.J. 2006. Haze formation in beverages. LWT 39, 987994. Sims, C.O., and Morris, J.R. 1986. Effects of acetaldehyde and tannins on the color and chemical age of red muscadine, Vitis rotundifolia, wine. J in all. Vitek. 37, 163165. Skouramaunis, G.K., Kwiatkowski, M., Sefton, Emma, Gorel, R. and Waters, E.J. 2003. In situ measurement of white wine absorbance in clear and in colored bottles using a modified laboratory spectrophotometer. Ost J. Grape Wine Res. 9, 138148. Skouramaunis, G.K., Kwiatkowski, M.J., Francis, I.L., Oki, H., Carpone, D.L. Peng, Z., Duncan, B., Sefton, Emma, and Waters, E.J. 2005. The influence of ascorbic acid on the composition, color and flavor properties of a Riesling and a wooded Chardonnay wine during 5-year sapos storage. Ost. J. Grape. Wine Res. 11, 355368. Smith, A. K., and Noble, A. C. 1998. Effects of increased viscosity on the sourness and astringency of aluminum sulfate and citric acid. Foodquill. Brief. 9, 139144. Summers, T.C. 1982. Pigment Phenomena, From Grapes to Wine. In Grape and Wine Centennial Symposium Proceeding S, A. D. Webb, ed. pp. 254257. University of California, Davis. Summers, T.C. 1998. The Wine Spectrum. Wine Titles, Adelaide, Australia. Summers, T.C., and Evans, M.E. 1974. Wine Quality, Correlations with Color Den. Site and anthocyanin equilibria in a group of young red wine. JSCI. Food. Agric. 25, 1369 1379. Summers, T.C., and Evans, M.E. 1977. Spectral Evaluation of Young Red Wines. Anthocyanin equilibria, total phenolics, free and molecular SO2 chemical. Age. JSCI. Food Agric. 28, 279287. Chapter 2, Visual Perceptions 52. Summers, T.C., and Z. Emleys, G. 1985. Flavanol haze in white wines. Vitis 24, 4350. Squire, L.R., Bloom, F.E., Spitzer, N.C., Dulac, S., Ghosh, A., and Berg, D. eds. 2008. Fundamental Neuroscience, 3rd ed. Academic Press, San Diego, CA. Tromp, A., and Van Wyk, C.J. 1977. The Influence of Color on the Assessment of Red Wine Quality. In Proceeding of the South African Society of Enology and Viticulture, pp. 107117. Waters, E.J., Peng, Z., Pocock, K.F., and Williams, P.J. 1996a. Lacquer-like bottle. Deposits in red wine. In Proceedings of the 9th Australian Wine Industry Techni. Cal Conference, S. Stockley et al., eds, pp. 3032. Wine Titles, Adelaide, Australia. Waters, E.J., Shirley, N.J., and Williams, P.J. 1996b. Nuisance proteins of wine. Are grape pathogenesis-related proteins? J. Agric. Food Chemistry. 44, 35. Wenzel, K., Dietrich, H.H., and Heimfarth, M. 1987. Die Zusammensetzung der Anthocyanin in den verschiedenen Rebsorten. Vitis 26, 6578. Williams, A., Langren, S.P., and Noble, A.C. 1984a. Influence of Appearance of the Assessment of Aroma in Bordeaux Wines by Trained Assessors. J. Inst. Brew. 90, 25253. Williams, A., Langren, S.P., Timberlake, C.F., and Backer, J. 1984b. Effective color on the assessment of ports. J. Food Technol. 19, 659671. Yam, K.L., and Papadakis, S.E. 2004. A simple digital imaging method for showing and analyzing color of food surfaces. J. Food Engine. 61, 137142. Zampini, Z., and Spence, C. 2005. Modifying the multisensory perception of a carbonated beverage using auditory cues. Foodquill. Pref. 16, 632641. Zellner, D.A., and Whitten, L.O. 1999. The Effect of Color Intensity and Appropriateness on Color-Induced Odor Enhancement. J. Psychol. 112, 585604. References 53. This page intentionally left blank. Olfactory sensations. Chapter contents. Olfactory system 56. Nasal passages 56. Olfactory epithelium, receptor neurons, and cerebral connections 58. Odorants and olfactory stimulation 65. Chemical compounds involved 68. Acids 69. Alcohol 69. Aldehydes and ketones 69. Acetals 70. Esters 70. Hydrogen sulfide and organosulfur compounds 71. Hydrocarbon derivatives 72. Lactones and other oxygen heterocycles 73. Terpenes and oxygenated derivatives 73. Phenolics 74. Pyrazines and other nitrogen heterocyclics 75. Sensations from trigeminal nerve 75. Vomeronasal organ 76. Odor perception 77. Sources of variation in olfactory perception 87. Odor assessment in wine tasting 97. Off-odors 98. Acetic acid, volatile acidity 99. Baked 99. Buttery 99. Corky / moldy 99. Ethyl acetate 100. Ethyl phenols 100. Chapter 3. 55. Wine Tasting, a Professional Handbook, 2nd edition. Copyright #2009 by Academic Press, Incorporated. All rights of reproduction in any form reserved. Fusel 101. Geranium-like 101. Light-struck 101. Mousy 101. Oxidation 102. Reduced sulfur odors 103. Sulfur odor 104. Untypical aging flavor, Untypische Alterungsnot, UTA, 104. Vegetative odors 104. Other off odors 105. Chemical nature of varietal aromas 105. Olfactory system. Nasal passages. The olfactory region consists of two small patches recessed in the upper portion of the nasal passages, Fig. 3.1. Volatile compounds reach the olfactory epithelium either directly, via the nostrils, orthonasally, or indirectly, from the back of the throat, retronasally. The latter route is important in generation of what is termed flavor, the cerebral construct from the modalities of taste, touch, olfaction, and vision. The nasal passages are bilaterally divided by a central septum into right and left halves. The olfactory patches, epithelium, cover a small portion of the nasal cavity below the cribriform plate, on either side of the septum, just behind the eyes and midway between the ears. The receptor cells in each patch send signals, via perforations in the skull, cribriform plate, to Figure 3.1 Olfactory system. A. Location of the olfactory region in the nasal cavity and B. An enlarged section, not to scale, showing the olfactory neurons, receptors, and their connections to the olfactory bulb. From Jackson, 2008, reproduced by permission. Chapter 3, Olfactory Sensations 56. Corresponding halves of the olfactory bulb. The olfactory bulb is located directly above the olfactory epithelium, at the base of the skull. Some experiments suggest that the right hemisphere may possess greater odor discrimination than the left hemisphere, Zucco and Tresoldi. 1988. Alternatively, this may result more from the better airflow past the olfactory patches in the right than left nostril, Jowett al. 2004. Each nasal passage is further incompletely subdivided transversely by 3 outgrowths, the turbinate bones, Jowett al. 2004. These increase contact between the epithelial lining of the nasal passages and incoming air. These baffle-like bones induce turbulence, warming, and cleaning of the air, but also restrict airflow to the olfactory regions, located above the superior turbinate. It is estimated that during ordinary breathing, only about 5 to 10% of inhaled air passes over the olfactory patches. Hahn et al., 1993. Zhao et al., 2004. Even at high rates of air intake, the value may increase to only 20%. Although higher flow rates may enhance odor perception. Sobel et al., 2000, the duration, Fig. 3.2, number, or interval between sniffs, Fig. 3.3, apparently does not affect perceived odor intensity. The Figure 3.2. The perceived intensities, expressed as millimeter along a scale of 3 concentrations, C1, C2, and C3, of each of 3 odorants plotted as a function of the duration of a sniff, from Lang, 1986, reproduced by permission. AB. Figure 3.3. Arithmetic means of estimates of the perceived odor intensity of different concentration of pentyl acetate. These were obtained by having subjects use their natural sniffing technique, or 1, small black square, 3, 5, or 7, natural sniffs, b, natural sniffing, or 3, natural sniffs separated by intervals of 0.25 s, small black square, 0.5 s, 1.0 s, and 2.0 s. From Lang, 1983, natural sniffing gives optimum odor perception for humans. Perception 12, 99117, Pion Limited. London, reproduced by permission. Olfactory System 57. Usual recommendation to take short, swift sniffs probably has more to do with avoiding odor adaptation than enhancing odor perception. Only a fraction of the aromatic molecules that reach the olfactory patches is absorbed by the mucus that coats the epithelium. Of these molecules, only a proportion probably diffuse through the mucus and reach reactive sites on the olfactory receptor neurons. In some animals, high concentrations of cytochrome-dependent oxygenases accumulate in the olfactory mucus. Dahl, 1988. These enzymes catalyze a wide range of reactions and may increase the hydrophilic properties of odorants or facilitate their release from the mucus coating of the olfactory epithelium. These enzymes may also interact with olfactory UDP glucuranosyl transferase to catalyze reactions hypothesized to terminate olfactory activation. Lazard et al., 1991. The mucus layer is thought to be recycled about every 10 minutes. Olfactory epithelium, receptor neurons, and cerebral connections. The olfactory epithelium consists of a thin layer of tissue covering an area of about 2.5 centimeters, 2 on each side of the nasal septum. Each region contains about 10 million receptor neurons and associated supporting and basal cells. Fig. 3.4. Receptor neurons are specialized nerve cells that respond to aromatic compounds. Supporting cells, and the glands underlying the epithelium, produce a special mucus and several classes of odorant-binding proteins. Hrant et al., 1995, Garibaldi et al., 1997. A major constituent of the mucus matrix is olfactomedin. This protein is thought to act as a Trophic factor, activating growth and differentiation of olfactory neurons. Figure 3.4. Drawing of the olfactory neuroepithelial layer. From Lancet, D. 1986. With permission from the Annual Review of Neuroscience Volume 9. 1986 Biannual Reviews, www.annualreviews.org. Chapter 3, Olfactory Sensations 58. Another protein typically found in the mucus is an odorant binding protein, OBP. It is a soluble lipophilic protein produced by Bowman's glands. It possesses selective specificity for reversibly binding with a range of odor. Ants, Briandit al. 2002. The solubility of the complex is thought to assist the transport of hydrophobic odorants across the mucus to receptor sites. On olfactory cilia, Fig. 3.5. They may also assist in the deactivation of odorants. Its presence may partially explain the concentration of odorant molecules, 10�3 to 10⁴-fold, higher in the nasal mucus than in the inflowing airstream, Senfit al. 1980. Although humans appear to produce only a syn GLEOBP, other animals may produce several. Rats, rabbits, and pigs produce 3, whereas porcupines produce 8. Their enzymatic activity may also limit microbial growth and their access to the brain via the cribriform plate. Basal cells differentiate into receptor neurons and replace them as they degenerate. Receptor neurons remain active for an indifferent period, aging about 60 days, but possibly functioning for up to 1 year. Differentiate. Ing basal cells produce extensions that grow upward through the cribriform plate to connect with the olfactory bulb at the base of the brain. These non-myelinated extensions, axons, associate into bundles as they pass through the cribriform plate. In humans, olfactory and gustatory neurons are the only nerve cells known to regenerate regularly. Supporting cells electrically isolate adjacent receptor cells and are thought to maintain normal function. Figure 3.5. Scanning electron micrographs of the human olfactory mucosal surface and olfactory dendritic knobs and cilia. Photos courtesy of Drs. Richard M. Costanzo and Edward E. Morrison, Virginia Commonwealth University. Evidence is accumulating that nerve growth also occurs in the adult human brain. Olfactory system 59. Olfactory neurons show a common cellular structure. Thus, odor quality, the unique perceived characteristics of an odorant, is not associated with any obvious cellular differentiation of receptor neurons. Odorant/receptor interaction is believed to occur on the dendritic extensions, cilia, that develop on the surface of receptor cells, Fig. 3.50. The cilia project from a terminal swelling of the receptor cell, termed the olfactory knob. Fig. 3.5b. Each knob possesses up to 21 to 2 mm long, hair-like cilia. These markedly increase the surface area over which odorants can react with odor-binding proteins on the receptor membrane. Odorant molecules may bind to one, or more, different types of olfactory receptor, or proteins. The OR proteins are located in and transverse the membrane of the receptor neuron. Binding of the odorant with an OR protein activates adenylate cyclase, liberating cyclic AMP. It, in turn, activates the opening of ion channels in the membrane, resulting in an influx of Na and Ca2+. Murrell and Hunter, 1999. This initiates membrane depolarization and impulse transmission along the nerve fiber, eventually activating the olfactory centers in the brain. The distinctive character, quality, of a particular odor is thought to arise from the differential sensitivity of receptor neurons and the learning of their response pattern. Sensitivity reflects the presence of a unique family of odor-binding proteins produced by the olfactory epithelium, Buck and Axel. 1991. Each receptor cell expresses one of about 340 different odorant receptor genes. 2, Malnick et al., 2004. Thus, each receptor neuron produces but a single type of or protein. The olfactory receptor gene cluster constitutes the largest known gene family in mammals, Fuchs et al., 2001, and may constitute about 1 to 2% of the human genome, Buck, 1996. The proteins possess 7 domains, each of which spans the cell membrane. Their presence on the olfactory cilia ideally positions them to associate with odorants. Each odor-binding protein bears several variable regions, domains, which may act jointly to bind a particular reactive grouping, ligand, for example, a ring or hydroxyl structure. That individual receptor proteins possess several domains means that each receptor cell can potentially be simultaneously activated by different odorants possessing the same ligand. Correspondingly, different ligands of an odorant may activate sites on more than one type of receptor neuron, Fig. 3.6. Depending on the compound. Odor quality may depend on the combination, Fig. 3.7, and activation sequence of several different receptor neurons. Thus, for most aromatics, 2 there are also about 600 or pseudogenes, inactive gene sequences having similarity to and probably derived from active equivalents. Chapter 3, Olfactory Sensations 60. There is no simple correlation between odorant chemical structure and odor quality. Odor quality seems analogous to playing a piano scale. The sequence of notes and their intensity generate a distinctive pattern. The memory of this pattern appears to be encoded in the piriform cortex. In addition, changing the concentration of a compound may modify the pattern of receptor activation, altering its perceived quality. Grosisarov and Lancet, 1988. Although there are probably limits to discrimination, it appears that the primary controlling factor is need. Lee et al., 2008, enhanced significance can lead to improved discriminatory ability. Receptors for specific chemical structures tend to be organized into spatially distinct, but overlapping regions in the olfactory epithelium. Johnson and Leon, 2007. The selective reproduction of special subsets of receptor cells is thought to account for the increased sensitivity to an odorant on repeat exposure, Wysocki et al., 1989. This property is apparently a general characteristic of women during the childbearing years, but uncommon in men, Fig. 3.8. On stimulation, the electrical impulse rapidly moves along the filamentous extensions of the receptor neuron toward the olfactory bulb. They are Figure 3.6 Comparison of the receptor codes for odorants that have similar structures but different odors. Aliphatic acids and alcohols with the same carbon chains are recognized by different combinations of olfactory receptors, S1S86, thus providing a potential explanation for why they are perceived as having strikingly different odors. Perceived odor qualities shown on the right were obtained from Arctander, 1969, The Good Sense Company, http://www.thegoodscentscompany.com/right/ and the ChemFinder web server, http://chembiofinderbeta.cambridgeasoft.com/, from Malnick et al., 1999, reproduced by permission. Olfactory System 61. The only sensory neurons that directly synapse with the forebrain, without initially passing via the thalamus. In the olfactory bulb, bundles of receptor axons terminate in spherical regions called glomeruli, Fig 3.1b. Most evidence indicates that the axons innervating a particular glomerulus come from olfactory receptors activated by the same ligand, Tazaki et al., 2004. The spatial distribution of these glomeruli appear to reproduce the pattern of olfactory receptors in the olfactory epithelium, Johnson and Leon, 2007. Within the glomeruli, the axons synapse with one or more of several types of nerve cells, mitral and tufted cells, in the olfactory bulb. The olfactory bulb is a small, bilaterally lobed portion of the brain that collects and edits information received from receptor cells in the nose. This initially seems to involve the action of granule cells, to which mitral and tufted cells connect. They are thought to be involved in feedback inhibition of receptor neurons, as well as being activated by feedback responses from higher centers in the brain. This modulation may partially explain why the qualities of odor mixtures may differ from that of their individual components. Christensen et al., 2000. Intriguingly, granule cells show relative survival rates based on exposure to particular odors, Lado and Guerzi, 2003. These changes appear to partially explain why memory of wine odors improves with frequent exposure, but may subsequently deteriorate. Mitral cell development in the olfactory cortex is also associated with odor learning. Wilson et al., 2004. From the olfactory bulb, impulses are sent posteriorly, via the lateral olfactory tract, to the piriform olfactory cortex. In the latter, mitral cells from different glomeruli converge, combining the impulses from multiple receptor types, Zhu et al., 2001. The convergence is enhanced by an elaborate system of interconnections. For example, odorant mixtures can stimulate neurons in the piriform cortex not activated by their individual components, Zhu and Buck, 2006. This may also play a role in explaining Figure 3.7 model for the combinatorial receptor codes for odorants. The receptors shown in color are those that recognize the odorant on the left. The identities of different odorants are encoded by different combinations of receptors. However, each olfactory receptor can serve as one component of the Combinatorial receptor codes for many odorants. Given the immense number of possible combinations of olfactory receptors, this scheme could allow for the discrimination of an almost unlimited number and variety of different odorants, from Malnick et al., 1999. Reproduced by permission. Chapter 3, Olfactory Sensations 62. Why odorant mixtures may possess odor qualities distinct from their component constituents. Extended exposure to an odorant tends to result in adaptation. This apparently involves inactivation of fur-ing in the piriform and orbitofrontal cortex, Fig. 3.9. By suppressing the perception of persistent, background, odors. Best and Wilson, 2004, adaptation has the benefit of facilitating the detection of aromatic changes in the environment. Kadahisa and Wilson, 2006. The multiple synaptic connections in the olfactory, piriform, cortex is thought to facilitate the developing and encoding odor memories. Identification appears to take place in the anterior portion, whereas qualitative groupings, such as fruity /floral, edible versus nundable, appears to be localized in the posterior portion. Gottfried et al., 2006. From the olfactory cortex, signals pass to and from the thalamus, an integrator, the amygdala, associated emotion-related memories and social interactions, the occipital cortex, involved in memory consolidation, and on to higher centers in the brain, notably the orbitofrontal cortex. It is in the orbitofrontal cortex that neurons from the taste, odor, and visual centers of the brain converge and interact, Fig. 3.10, what is termed multisensory perception. Nerve cells develop expanded synaptic connections based on repeat, coincident, activation, the fire together, wire together concept. When an olfactory pattern is recognized, it simultaneously recalls other memories with which it developed, for example, the affiliation of vanilla with sweetness, the smell of Jewers Traminer with lychee nuts, or the fragrance of thyme with Christmas turkey. In the past few years, clear evidence has established that such associations are learned. Prescott, 2004. Stevenson et al., 1999, showed that odor ants with the strongest connection with sweetness have the greatest 1, 2, 3, 4, 5, 6, 7, 0, 8, 6. Benz, M. Log. Threshold. Concentration. Millimeter. Benz, F. AA, M. AA, F. MFF, M. MFF, F. 8. Test session. 10-0-12-42. Figure 3.8 Gender effects of repeated test exposures to benzaldehyde on mean benzaldehyde and control thresholds. Although initial thresholds for naive and experienced volunteers differed, the changes over trials did not, and thus data from the two groups were combined. Two-way, repeated measures ANOVAs with gender as the between-group factor showed a significant interaction between group and time, F. 9.90 equals 3.29, p 0.001, reprinted. by permission from Macmillan Publishers Limited, Nature Neurosci. Dalton, P., Doolittle, N., and Breslin, P.S. 2002. Gender. Specific induction of enhanced sensitivity to odors. 5. 199200. Olfactory system 63. Influence on enhancing the sweet taste of sugars. The same aromatics also had the greatest influence in reducing the perceived sourness of citric acid. Figure 3.11 illustrates the effect of strawberry odor on sweetness. Conversely, sweetness and other tastants can influence the perception of fruitiness in aromatic compounds. Cook et al., 2003. However, as with other learned linkages, lack of repeat stimulation, or disassociation of integrated sensations in the future exposures, can lead to a breakdown of the neuronal connections between sensory modalities. The integration of sensory modalities into the holistic percept called flavor appears to occur in the orbitofrontal cortex. The stability of such affiliations, Stevenson et al., 2003, probably explains why identification of tastants in gustatory odor mixtures may be poorer when critical components are missing. Lang et al., 2002, why aromatic compounds may appear to possess gustatory attributes, and tastants influence perceived aroma intensity. Dalton et al. 2000. Connections to the amygdala probably generate the emotional memory, or is often associated with certain odors, for example, those connected with childhood recollections. Individual cortical neurons can be associated with both specific odor memories and their perceived quality. Rolls et al., 1996. The neuroanatomy and psychophysiology of flavor perception are currently very active and dynamic areas of research. Wilson and Stevenson, 2006. 36. 0.4. 0.3. 0.2. 0.1. 0.1. 0. 0.20. 0.15. 0.10. 0.05. 0.05. 0. Behavior. ABC. Piriform cortex, orbitofrontal cortex. 30. Intensity. Rating. 0. 100%. Signal. Change. Percent. Signal. Change. Time, successive 30s blocks. Time, successive 30s blocks. Time, successive 30s blocks. 24. 18. 1 2 3 4 5 6 7 1 2 3 4 5 6 7 1 2 3 4 5 6 7. Figure 3.9 Behavioral and neural effects during within-session habituation to the target odorant. Over the 3.5 minutes period of habituation, odor intensity rating progressively declined. Neural responses in the right posterior piriform cortex, B, and left olfactory orbitofrontal cortex decreased from the first to the last time block, paralleling the intensity rating profile, reproduced from Lee, W., Luckenberg, E., Parrish, T., and Gottfried, J. 2006. Learning to smell the roses, experience-dependent neural plasticity in human piriform and orbitofrontal cortices. Neuron 52, 1097 1108, with permission from Elsevier. Chapter 3, Olfactory Sensations 64. Odorants and olfactory stimulation. There is no precise definition of what constitutes an olfactory compound. Based on human perception, there are thousands of olfactory substances, involving many chemical groups. For air-breathing animals, an odorant. Figure 3.10 schematic diagram of the taste and olfactory pathways in primates, including humans, showing they converge with each other and with visual pathways. The gate functions shown refer to the finding that the responses of taste neurons in the orbitofrontal cortex and the lateral hypothalamus are modulated by hunger, VPMPC, ventral posteromedial thalamic nucleus, VPL, ventral posterolateral nucleus, V1, V2, and V4, visual cortical areas, reproduced from Rolls, E.T. 2005. Taste, olfactory, and food texture processing in the brain, and the control of food intake. Physial. Behave. 85, 45, 56, with permission from Elsevier. Odorants and olfactory stimulation 65. Must be volatile, pass into a gaseous phase at normal temperatures. Although this places an upper limit on molecular size. 300 Daltons, low molecular weight implies neither volatility nor aromaticity. Most aromatic compounds have strong hydrophobic, fat-soluble, and weak polar water-soluble sites. They also tend to bind weakly with cellular constituents and dissociate readily. More difficult than explaining aromaticity is odor quality. Odors may be generated by single compounds or be the overall reaction to many compounds. The latter is typical for natural objects, such as flowers and fruit. Wine, for example, may possess more than 50 compounds that occur at sufficiently high concentrations to directly affect its odor. As noted, odor memories appear to be stored as holistic integrated patterns, its odor gestalt, based on experience, context, attention, expectation, and intensity, not on a collection of readily separable sensations. Wilson and Stevenson, 2003. Wine fragrance and flavor are much more than just the sum of their parts. They are cerebral constructs. For example, we learn to associate certain olfactory sensations with particular colors and wine types. Subsequently, knowing the varietal nature of a wine will induce a search for, and possibly distort, sensory inputs to match expectations. Tasters may use the reverse process to confirm suspected varietal, regional or stylistic origins of a wine. Depending on the degree of fit, tasters will have varying degrees of success in recognizing a wine's origin. The relative degree of similarity appears to explain the frequent addition of the suffix like or y to wine descriptors, for example, rose-like, apple-like, grassy, barnyardy. They evoke similarities, but usually not exact identities. This is the equivalent of searching for unusable patterns in images, Fig 3.12, or the diversity of objects that can be imagined in an inkblot or cloud. The ability of the mind to interpret the same data differently. Figs 3.13 and 6.4 may also explain why the same wine may alternately show a diversity of apparently distinct fragrances. Figure 3.11 perceived sweetness as affected by The presence or absence of fragrance, from Frank and Byram, 1988, reproduced by permission. Figure 3.12 Example of Gestalt. Perception. The image initially appears as a random set of black patches on a white background. With continued observation, a Dalmatian dog sniffing the ground with a tree trunk in the background suddenly appears. This sudden interpretation is dependent on one possessing in memory the shape of a dog. Despite repeated efforts, we have been unsuccessful in our attempts to locate the photographer on James or the original source of this image. Please contact the publisher if you have questions regarding the use of this image. Chapter 3, Olfactory Sensations 66. It appears that several molecular properties may be involved in olfactory stimulation, Olof, 1986. They include electrostatic attraction, hydrophobic bonds, van der Waals forces, hydrogen bonding, and dipole-dipole interactions. Small structural cations, such as those found in stereo isomers, can markedly affect the relative intensity and perceived quality of related odorants. For example, D and L carvone stereoisomers possess spearmint-like and caraway-like qualities, respectively. Compounds belonging to the same chemical group may show competitive inhibition, despite possessing different odor qualities. Pierce et al. 1995. This phenomenon, called cross-adaptation, results in suppressed detection of one odorant by prior, or simultaneous, exposure to a related odorant. The phenomenon tends to dissipate with extended exposure. Lawless, 1984a. This can result in the unmasking of compound S, whose presence was suppressed. This phenomenon and forward/or progressive changes in the composition of headspace gases are presumably involved in the development of a wine's aromatic attributes throughout the course of a tasting. As the aromatic composition of a wine changes and sensitivity of the olfactory receptors changes, the aroma profile generated may trigger different odor memory patterns, resulting in the recognition of new attributes. Mixtures of aromatic compounds often lose their individual identities or are detected at diminished intensities. Suppression has been shown to occur at the level of olfactory reception in the nose, where members of diverse chemical groups may antagonize activation of specific receptor proteins. Sands et al., 2006. However, at low concentrations, synergistic effects. Figure 3.13 Example of a perception set. The viewer can visualize an illustration of an old lady or a young woman in sequence, but never at the same time. It was first used as an example of perceptual set in the 1930s by Edwin G. Boring and subsequently by Leeper, 1935. It seemingly was first published by the British cartoonist W. E. Hill in 1915, but may be based on an earlier French version produced in 1888. Odorants and olfactory stimulation 67 have also been detected, Fig 3.14. This can benefit detection of desirable aromatics, but may also enhance the perception of off odors. Lang et al., 1994. An expression of the complexity of these reactions is given by Piggott and Findlay. 1984. They found both synergistic and suppressive influences with different pairs of esters, with even opposite effects appearing at different concentrations. Synergistic effects can even occur across modalities, such that the combination of subthreshold concentrations of olfactory and gustatory compounds can result in detection of both. Dalton et al., 2000. This phenomenon appears to occur only with sensations that already have been integrated through experience. Breslin et al., 2001. These reactions, combined with human variability in sensitivity, partially explain why people differ so frequently in their responses to wines. Chemical compounds involved. The major chemical constituents in wine, alcohols, acids, phenolics, tend to generate gustatory rather than olfactory sensations. In contrast, minor or trace constituents donate a wine's distinctive aromatic characteristics. For example, the most common wine phenolics, for example, tannins, elicit taste and trigeminal sensations, whereas trace phenolics, for example, vinyl phenols, SYR, ingaldehyde, have aromatic properties. The primary exception is ethanol. Although principally inducing mouth-feel sensations, ethanol also possesses a mild but distinctive odor. Volatility, an essential attribute of an odorant, is influenced by many factors. One of the more important involves the non-volatile constituents of a wine. For example, mannoproteins may bind important flavorants, such as bianon, ethylhexanoate, and octanol, but enhance the volatility of others, such as ethyloctanoate and ethyldecanate. Lubbers et al., 1994. Sugars, Sorrentino et al., 1986, Oils, Roberts et al., 2003, Various macromolecules, Voily et al., 1991, Polyphenolics, Aronson and Ibila, 2004, and Ethanol, Sakaki et al., 2005, can also influence volatility. Figure 3.14 mean thresholds of detection for 1-butanol, 2-pentanone, and N-butyl acetate alone. And in a mixture of all three compounds, small black square. Data from 40 subjects, from Patterson et al., 1993. Reproduced by permission. Chapter 3, Olfactory Sensations 68. Acids. The most significant of volatile acids, acetic acid, is also the most common. Other volatile acids, such as formic, butyric, and propionic acids occur, but seldom at above threshold levels. All these acids have marked odors. Acetic acid being vinegary, formic acid having a strong pungent odor, propinic acid possessing a fatty smell, butyric acid resembling rancid butter, and C6 to C10 carboxylic acids possessing goaty odors. Correspondingly, volatile acids are typically associated with off odors. A partial exception is acetic acid. It can add complexity to the bouquet at threshold levels. Above its recognition threshold, 300 mg/liter, though, it becomes a major fault. The major wine acids, notably tartaric and malic, are non-volatile. Lactic acid has a mild odor, but is seldom of sensory significance. These acids may indirectly play a role in wine fragrance by participating in the formation of aromatic esters, alcohols. The mild fragrance of ethanol has already been noted. Nevertheless, the most significant aromatic alcohols are higher alcohols. These are chemically related to ethanol but have carbon chains 3 to 6 carbons long. Examples, such as 1-propanol, 2-methyl-1-propanol, isobutyl alcohol, 2-methyl-1-butanol, and 3-methyl-1-butanol, isomal alcohol, tend to have fusel odors, whereas hexanols possess a herbaceous scent. The major phenol-derived alcohol, 2-phenylethanol, phenethyl alcohol, has a rose-like aspect. The higher alcohols most commonly found in wine have a strong pungent odor. At low concentrations, 0.3 g/liter or less, they may add to the complexity to the bouquet. At higher levels, they increasingly dominate the fragrance. In distilled beverages, such as brandies and whiskies, fusel alcohols give the beverage much of its distinctive fragrance. It is only in port that a fusel character is considered a positive quality attribute. This property comes from the fortifying spirits added during its production. Although most higher alcohols are yeast byproducts, the fungus B. cinerea produces an important alcohol, 1-octan-3-ol, Rapp and Guntert, 1986. Not too surprisingly, it is characterized by mushroomy odor. Aldehydes and ketones. Acetaldehyde is the major vinous aldehyde. It often constitutes more than 90% of the wine's aldehyde content, above threshold values in table wines. Chemical compounds involved 69. Acetaldehyde is considered an off-odor. Combined with other oxidized compounds, it contributes to the traditional bouquet of sherries and other oxidized wines. Furfuryl and 5-hydroxymethyl, 2-furaldehyde are other aldehydes having a vinous sensory impact. Their caramel-like aspects are most evident in baked wines. Phenolic aldehydes, such as cinnamaldehyde and vanillin, may accumulate late in wines matured in oak. Other phenolic aldehydes, such as benzaldehyde, may have diverse origins. Its bitter almond odor is considered characteristic of certain wines, for example, those from Gomery grapes. Although not having a direct sensory effect, hydroxypropanediol, triose reductone, characteristically occurs in botrytized wines, Gillow et al. 1997. It exists in tautomeric equilibrium between 3-hydroxy-2-oxypropanol and 3-hydroxy-2-hydroxypro-2-enol. Reductones, such as hydroxypropane diol, can play a role in preserving a wine's fragrance by fixing, slowing volatile loss of its aromatic constituents. Many ketones are produced during fermentation, but few appear to have sensory significance. The major exception is diacetyl, biacetyl, or 2,3-butanediene. At low concentrations, diacetyl denotes a buttery, nutty, or toasty flavor. However, at much above its sensory threshold, diacetyl generates a buttery, lactic off-odor. This commonly occurs in association with spoilage induced by certain strains of lactic acid bacteria. Acetals. Acetals form when an aldehyde reacts with the hydroxyl groups of two alcohols. They generally possess vegetal odors. because they form primarily during oxidative aging and distillation. They tend to occur only in significant amounts in sherry or in brandies. Esters. More than 160 esters have been isolated from wine. Because most esters occur only in trace amounts and have either low volatility or mild odors, their importance to wine fragrance is negligible. However, the more common esters may occur at or above their sensory threshold. Because some of them have fruity aspects, they can be an important factor in the bouquet of young wines. Their influence tends to be comparatively short-lived as they break down during aging to their constituent acid and alcoholic components. The most significant esters found in wine are formed between ethanol and short-chain fatty acids, acetic acid and various short-chain alcohols. Chapter 3, Olfactory Sensations 70. And non-volatile acids and ethanol. Several other ester groupings occur, but in most instances they have no sensory significance. Ethyl acetate, formed between ethanol and acetic acid, is the most significant ester in wine. In sound wines, its concentration is generally below 50 to 100 mg/liter. At low levels, 50 mg/liter, it may add to a wine's complexity. At contents above 150 mg/liter, ethyl acetate generates an acetone. Like off-odor, Amarine and Rosella, 1983. It is a metabolic byproduct of microbial metabolism, both yeast and bacterial, and can form abiotically by a reaction between acetic acid and ethanol. Other than ethyl acetate, the major ethanol-based esters are those formed with higher alcohols, such as isomal and isobutyl alcohols. These lower molecular weight esters are often termed fruit esters because of their fruit-like fragrances. For example, isomal acetate, 3-methylbutylase tate, has a banana-like scent, and benzyl acetate an apple-like aspect. They play a significant role in the bouquet of young wines, notably white wines. Vernon et al., 1986. As the length of the hydrocarbon chain of the acid increases, the odor shifts from being fruity to soap-like and, finally, lard-like. With C16 and C18 fatty acids. The presence of certain of these esters, for example, hexyl acetate and ethyl octanoate, has occasionally been considered an indicator of red wine quality. Murray et al., 1979. Esters of the major fixed acids in wine, tartaric, malic, and lactic, form slowly during aging. Nevertheless, because of their weak odors, they are seldom of sensory significance. In contrast, the formation of the methanolic and ethanolic esters of succinic acid appears to contribute to the aroma of muscadine wines. Lemiconera et al., 1996. Occasionally, other esters of significance may be found in grapes. The phenolic ester, methylanthranilate, is a prime example. It contributes to the grapey essence of most V. labrusca varieties. Another is ethyl-9-hydroxy nonanoate, synthesized by B. cinerea. It may contribute to the distinctive aroma of botrytized wines. Marjuda et al., 1984. Hydrogen sulfide and organosulfur compounds. Hydrogen sulfide and sulfur-containing organics generally occur only in trace amounts in bottled wine, thankfully so. They usually have unpleasant and to nauseating odors. However, because their sensory thresholds are typically low, often in parts per trillion. They occasionally generate off odors. Hydrogen sulfide, H2S, is a common byproduct of yeast sulfur metabolism. At near threshold levels, hydrogen sulfide is part of the yeasty odor of newly fermented wines. Above threshold levels, it generates a putrid, rotten egg off odor. Chemical compounds involved 71. The simplest organosulfur compounds found in wine are the mercap tans. A significant member is ethanethyl, ethyl mercaptan. It produces a rotten onion, burnt rubber odor at threshold levels. At higher levels, it has a skunky, fecal odor. Related thiols, such as 2-mercaptothanol, methanethiol, and ethanedithiol, have barnyard, rotten cabbage and sulfur rubber off odors, respectively. Exposure to light can stimulate the reductive synthesis of organosulfur compounds in bottled wine. An example is the cooked cabbage, shrimp like off odor generated by dimethyl sulfide in the Gout de Lumière taint of Champagne, Charpentier and Morgan, 1981. Although organosulfur compounds were first recognized as sources of off odors, an increasing number have been found crucial to varietal aroma of several grape cultivars. For example, several thiols contribute to the aroma of Sauvignon Blanc wines. These include 4-mercapto-4-methylpentantuol, 3-mercapto-hexan-1-ol, 4-mercapto-4-methylpentantu-1, 3-mercapto-hexyl acetate, and 3-mercapto-3-methylbutan-1-ol, Taminiga et al., 1996, 1998. 4-mercapto-4-methylpentantuol also plays a central role in the characteristic aroma of Scub, Guth, 1997b, and Macabeo, Escudero et al., 2004. Wines. Often these constituents occur as non-volatile complexes in grapes. It is the enzymic action of yeasts during fermentation that liberates the active ingredient. Another example of an important aromatic organosulfur compound is 3-mercaptohexan-1-ol. It is central to the fruity aroma of many rose wines. Murat, 2005. Hydrocarbon derivatives. Several hydrocarbons in grapes generate important volatile degradation products. Examples are B-damascenon, floral-like, A and B-ionon, violet-like, vitispirane, eucalyptus camphor-like, and 1,1,6-trimethyl 1,2-dihydronaphthalene, TDN. Several are derived from the hydrolytic degradation of carotenoids. Possibly the most significant hydrocarbon derivative is the norisopyr noid, TDN. After several years of in-bottle aging, the concentration of TDN can rise to 40 ppb, Rapp and Guntert, 1986, or above. At above 20 ppb it donates a smoky, kerosene, bottle-aged fragrance. Simpson, 1978. A cyclic hydrocarbon occasionally found in wine is styrene. It can produce a taint in wine stored in plastic cooperage or transport containers. Hamat-Shek, 1982. Additional hydrocarbon taints may come from methyl tetrahydronaphthalene, implicated in some types of corky off-odors, Dubois and Ragaud, 1981. Chapter 3, Olfactory Sensations 72. Lactones and other oxygen heterocycles. Lactones are cyclic esters formed by internal esterification between carboxyl and hydroxyl groups. Those coming from grapes seldom contribute varietal odors. However, one exception is 2-vinyl-2-methyl-tetrahydrofuran 5,1. It has been proposed as contributing to the distinctive aroma of Riesling and Muscat varieties, Schreier and Drouert, 1974. Because lactone formation is enhanced during heating, some of the raisined character of sun-dried grapes may come from lactones such as 2-pentanoic acid G-lactone. Cetolin, 4,5-dimethyl-tetrahydro-2,3-furandiene, is characteristic of botrytis infected wine, Marjuda et al., 1984, as well as sherries, Martin et al., 1992. It has a nutty, sweet, burnt odor. Lactones in wine may form during fermentation or aging, but the most common are extracted from oak. The most important of these are the oak lactones, isomers of B-methyl-G-octalactone. Yeasts may also synthesize them in small amounts. They possess oaky, coconut-like odors. Among other heterocyclic compounds, vitispirane appears to be the most significant. Etuvant, 1991. Vitispirane forms slowly during aging, reaching concentrations of 20 to 100 ppb. Its two isomers have different odors. The cis isomer has a chrysanthemum flower fruity odor, whereas trans-vitispirane has a heavier, exotic, fruit-like scent. Terpenes and oxygenated derivatives. Terpenes provide the characteristic fragrance of many flowers, fruits, seeds, leaves, woods, and roots. Chemically, terpenes are composed of two or more basic, 5-carbon, isoprene units. Unlike many other wine aromatics, terpenes are primarily derived from grapes, Strauss et al., 1986. Only those that occur free, unbound to sugars, contribute to wine fragrance. Terpenes contribute to the varietal character of several important grape varieties, most notably members of the Muscat and Riesling families, c. Rapp, 1998. A sesquiterpene, rotundum, has recently been identified as the source of the peppery aroma that frequently characterizes the aroma of Shiraz wines, Wood et al., 2008. Other cultivars produce terpenes, but they appear to play little role in their varietal distinctiveness. Strauss et al., 1987b. Although terpenes are unaffected by fermentation, grape infection by B. Cinerea both reduces and modifies their terpene content. This undoubtedly plays a major role in the minimal varietal character of most botrytist wines. Bock et al., 1988. During aging, the types and proportions of terpenes found in wines change significantly. Rapp and Guntert, 1986. Although some increase in chemical compounds involved 73. Sensory impact results from the breakdown of glycosidic bonds. Losses due to oxidation are more common. In the latter reactions, most monoterpene alcohols are converted to terpene oxides. These have sensory thresholds approximately 10 times higher than their precursors. In addition, these changes usually affect odor quality. For example, the muscati, iris-like odor of linalool is progressively replaced by the musty, pine-like scent of aterpeneal. During aging, additional changes can modify the structure of wine terpenes. Some terpenes become cyclic and form lactones, for example, 2-vinyl-2-methyl-tetrahydrofuran 5,1, from linalool oxides. Other terpenes may transform into ketones, such as A and B ion, or spireters, such as vitispirane. Although most terpenes have pleasant odors, some produce off odors. A prime example is the musky-smelling sesquiterpenes produced by Penny. Psyllium roquefortii in cork, Hyman et al., 1983. Streptomyces species may also synthesize earthy-smelling sesquiterpenes in cork or cooperage. Wood phenolics. The most important, grape-derived, volatile phenolic is methyl-anthrani. Late. It is a major aroma component of most Vitis labrusca varieties. Another significant volatile phenolic is 2-phenylethanol. It produces the rose-like fragrance typical of some V. rotundifolia cultivars. In many V. vinifera cultivars, it is part of the complex of aromatic compounds found in their wines. Although phenolics may contribute to the varietal aroma of a few cultivars, the most significant are the hydroxycinnamic esters generated during fermentation or derived from oak cooperage. Hydroxycinnamates can also be metabolized to volatile phenols by spoilage microbes. Their derivatives: vinyl phenols, 4-vinyl guaricol and 4-vinyl phenol, and ethyl phenols, 4-ethyl phenol and 4-ethyl guaricol, can donate spicy, pharmaceutical, clove-like odors, and smoky, phenolic, animal, stable-like notes, respectively. Off odors are frequently detected when ethyl phenol contents exceed 400 mg/liter, or 725 mg/liter for vinyl phenols. Eugenol, another clove-like derivative, can also occur in wine. At usual concentrations, eugenol adds only a general spicy note. Another derivative, guaricol, has a sweet, smoky odor. It is the source of some cork-derived off odors. Oak cooperage is the source of several volatile phenolic acids and aldehydes. Benzaldehyde is particularly prominent and possesses an almond-like odor. Its occurrence in sherries may participate in their nut-like. Chapter 3, Olfactory Sensations 74. Bouquet. Other important phenolic aldehydes are vanillin and syringaldehyd, both of which possess vanilla-like fragrances. They form during the breakdown of wood lignins, the toasting of oak staves during barrel construction is another source of volatile phenolic aldehydes, notably furfuryl and related compounds, pyrazines and other nitrogen heterocyclics. Pyrazines are cyclic nitrogen-containing compounds that contribute significantly to the flavor of many natural and baked foods. They are also important to the varietal aroma of several grape cultivars. 2-methoxy-3 isobutylpyrazine plays a major role in the bell, green, pepper odor, often detectable in Cabernet Sauvignon and related cultivars, such as Sauvignon Blanc and Merlot. At concentrations of about 820 ing/liter, methoxybutyl pyrazine may be desirable, but, at above these values, it starts to generate an overpowering vegetative, herbaceous aroma. Related pyrazines are present but generally occur at concentrations at or below their detection thresholds. Allen et al., 1996. Pyridines are another group of aromatic cyclic nitrogen compounds periodically isolated from wine. Thus far, their involvement in wine flavor appears to be restricted to the production of mousy off odors. This odor has been associated with 2-acetyl tetrahydropyridines, 2-ethyl tetrahydropyridine, and 2-acetyl-1-pyrroline, Heristin, 1986, Gbinit al., 1996. They are produced by some strains of Brettanomyces. Sensations from trigeminal nerve. Unlike the concentration of olfactory receptors, free nerve endings of the trigeminal nerve occur throughout the nasal epithelium, excepting the olfactory patches. The location and sensitivity of these receptors throughout the nasal passages is poorly understood but appears to be non-uniform. Frasnelli et al., 2004. The nerve endings respond primarily to low concentrations of a wide range of pungent and irritant chemicals. However, most odorant molecules can activate trigeminal receptors, usually at suprathreshold concentrations. Olof, 1994. Examples are benzaldehyde, cherry/almond, and isoamyl acetate, banana. Vanillin is apparently an exception. Savic et al., 2002. Odorants with trigeminal activity can potentially stimulate trigeminal receptors in the mouth as well. Both oral and nasal stimulation of trigeminal receptors by odorants may, thus, occasionally play a role in flavor identification during wine tasting. Sensations from trigeminal nerve. 75. Trigeminal receptors are generally less susceptible to adaptation than olfactory receptors, Kane, 1976. Because of their general responsiveness to chemicals, the trigeminal nerve engenders what is called the common chemical sense. Most pungent chemicals react specifically with sulfhydryl, or disulfide, SS, bridges of proteins, Kane, 1985. The reversible structural changes induced in membrane proteins probably stimulate the firing of free nerve endings. Most pungent compounds also tend to have a net positive charge. In contrast, putrid compounds commonly possess a net negative charge. Amor et al., 1964. Volatile compounds that are strongly hydrophobic may dissolve into the lipid component of the cell membrane, disrupting cell permeability and inducing nerve firing, Kane, 1985. Their stimulation elicits sensations such as irritation, burning, stinging, tingling, pain, and the general perceptions of temperature, viscosity, weight, and freshness. Not surprisingly, activation of free nerve endings can also modify the perceived quality of an odorant, making it unpleasant at high concentrations. For example, indole is jasmine-like at low concentrations, but fecal-like at higher levels, clean. 1986, and small amounts of sulfur dioxide can be pleasing, but at high concentrations are strongly irritant. Similarly, hydrogen sulfide contributes to a yeasty bouquet and fruitiness at low concentrations. 1 mg/liter. Macrosti, 1974, but at slightly higher concentrations donates a putrid, rotten egg odor. Trigeminal stimulants also tend to suppress the perception of pure olfactory compounds, those that do not stimulate trigeminal nerve endings. For example, carbon dioxide can suppress the detection of vanillin, cobalt, and Hummel, 1988. The importance of this phenomenon, if any, to the perception of sparkling wines appears to be unknown. Vomeronasal organ. The vomeronasal organ consists of a pair of small tubular cavities lined by chemoreceptive cells, near the opening of the nostrils, Moran et al., 1994. They respond to vomeropherins, volatile compounds that play important roles in animal social interaction. In humans, these structures appear to be vestiges. They are found infrequently, and when present are highly morphologically variable, Abomali et al., 2001. They appear to be non-functional in humans, Tritia et al., 2000. Correspondingly, it seems highly unlikely that the vomeronasal organ plays any role in wine perception. Chapter 3, Olfactory Sensations 76. Odor perception. Differences in odorant perception have long been known. What is now clearer is the extent of this variation. Pangborn, 1981. Variation can affect the ability to detect, identify, and sense odor intensity, as well as their emotional or hedonic response. The detection threshold is defined as the concentration at which the presence of a substance just becomes noticeable. Measurements given in the literature generally refer to when just over 50% of the test subjects detect the compound at about chance. Human sensitivity to various odor ants varies over 10 orders of magnitude, from ethane at about 2.10 m to between 1010 and 1012 m for mercaptans. Even sensitivity to the same, Fig 3.15, or chemically related compounds may show tremendous variation. For example, the individual detection thresholds of trichloroni, sol, TCA, and pyrazines span 4 and 9 orders of magnitude. Seifert et al., 1970. Examples of the thresholds of several important aromatics in wine are given in Table 3.1. Threshold values are significantly influenced by the solvent, for example, water versus ethanol. Ethanol, 10%, has been found to increase the detection threshold of ethyl isobutanoate from 0.03 mg/liter in water to 15 mg/liter. Guth and Size, 2002. This has been noted in the increased fruity and floral aspects of some esters at alcohol content below 8%. Guth, 1998. This may partially explain the more floral nature of Riesling wine from Germany, often produced at alcohol contents significantly below the 11 to 13% typical of most